Welcome to this talk on engineering a platform using Kubernetes operators. My name is Tom de Wolf and I'm a senior architect at ACA Group in Belgium. In this talk, we'll dive into how to raise the level of abstraction to provide a better self-service experience for developers. Raising the level of abstraction is an essential best practice for platform engineering. The goal of platform engineering is to lower the cognitive load for developers that want to create IT components like applications or others. There is a need to do this because there's just too much technology and infrastructure components involved to bother the developer with when he wants to deliver business value. How can we do this? By providing an easy self-service experience for that developer. And in that, the platform has the job to orchestrate everything and automate as much as possible and encapsulate that lower level complexity of the infrastructure and technologies. So raising the level of abstraction means that the self-service of that developer will be at that abstraction level and no longer at the individual infrastructure components or technologies that are involved. To be able to do that, to actually raise that abstraction level, you need to introduce a new vocabulary. And a good metaphor used also by Gregor Hope is that of a car. A car allows a driver to easily move around and is a great abstraction to lower the cognitive load. On the other hand, if it would be called a piston gear wheel assembly, that just reveals too much lower level complexity and it would not lower the cognitive load, but instead raise the cognitive load. So in order for us to raise the level of abstraction, you of course also need a tool in your toolbox to enable you to engineer a platform that actually introduces those abstractions. And in this section, I'll dive into Kubernetes and how Kubernetes can be used as a universal control plane to build such a platform. But first, let's dive into what the core component is that will enable this. And that's the Platform Orchestrator of your platform. To be the core layer in which the abstractions are brought to life and which actually contains the engineering of that platform that will do all the orchestration and automation. So on the one hand, it will provide APIs on which self-service experiences can be provided, and on top of which developer portals, CLIs, or other tools can be connected so that the developer can actually use that platform. On the other hand, you want to bring those abstractions that you have in those APIs alive by orchestrating and automating the complete lifecycle of such an abstraction. You want to hide all the complexity that's irrelevant from the infrastructure and technology plane beneath it. When we have a look at Kubernetes as a universal control plane, then it's actually a framework to build such platform orchestrators. It's an extensible, API-driven framework which allows you to, on the one hand, define, design an API and abstractions by using custom resource definitions or CRDs. And on the other hand, automation and orchestration is done by implementing your own custom Kubernetes operators that will act upon those custom resources and start automating things within the infrastructure and technology plane. So how does that work in detail? So when you want to design your API and your abstractions, you're going to use custom resource definitions. In Kubernetes, everything is a resource, and those resources are served as APIs on endpoints on the Kubernetes servers. Those APIs are declarative APIs. They express the desired state of that resource. So for example, if you take one of the default resources of Kubernetes, which is called a deployment, it allows you to specify that you desire 3 replicas of a certain container that you also specify in that resource. This is then deployed on Kubernetes, and Kubernetes itself will take over and start deploying all the containers that are needed to reflect that desired state. You can thus also define your custom resource definitions, which allows you to, in a certain group, define certain types of resources called a kind, and you can give it a name, for example, microservices. And using an open API specification, you can then specify which properties the developer can configure to define how that microservice should look like. And this ends up then in an API on which the abstraction of a microservice can be specified. Using the API is then manipulating and inspecting those resources. And that can be done by the kubectl CLI, like is shown here, where you apply new microservices or get the status of those new components, or by any other tool in the Kubernetes ecosystem that interacts with the REST API endpoints that are then available. To automate and orchestrate technologies and infrastructure components within your platform, you can use the Kubernetes operator pattern. If you consider the platform orchestrator or control plane and the environment or data plane in which the technologies and infrastructure components reside, then Kubernetes provides an API server through which the developers can use the APIs directly or through CLIs and user interface on top of it to actually create and manipulate the resources of Kubernetes. These are then stored within a document store, more specifically etcd, and those reflect the desired state of the platform that you want to achieve. Then a set of asynchronous operators will take that state to reconcile this state in the real world and make the environment look as the desired state. So that operator will run in a continuous reconciliation loop, and it will check what the delta is between the desired state of your resources and the actual state within the platform environment. When that manipulation of the state succeeds or fails, that again can be reflected and written as a status within those resources so that the developers can also inspect and follow what is happening within the platform. Such an operator is just a container running in Kubernetes, and it can be written in almost any language that can run within a Docker container. The goal is to write the orchestration logic within that reconciliation loop, and in some languages there are also operator SDK libraries available to make this easier. Also note that the data plane or the environment can be within Kubernetes itself, but it can also be outside of Kubernetes. And you can also orchestrate APIs of cloud services or other on-prem services as long as it has an API. The end result is that you have your platform orchestrator composed of one or more custom resource definitions that design and define those abstractions, operators that will act upon those abstractions and provision and orchestrate things within your environment or platform, and Kubernetes will serve those abstractions as APIs towards a self-service experience for your developers. Let's provide some example abstractions. First one is a microservice in the context of a software engineering task. A microservice typically consists out of a front end, a back end, and a database, and the interactions between those components. When you dive into the details of what that means on the technology and infrastructure level, there are a lot of components involved. And for the front end, there might be a separate Git repository. You might deploy it as a Kubernetes container. So you need a deployment, a pod, a service to make it accessible to the outside world, and maybe also a configuration in some kind of authorization server to make it secure. And for the database, there is, of course, the database schema that's used for that microservice with a user to access it securely, and the different tables that are provisioned within that database. You don't want the developer to go and specify and create each of those individual components. No, you want to raise the level of abstraction so that the developer can speak in terms of a microservice and specify the desired state, and that the platform translates everything towards those individual components. A microservice is then more than just a container, and you want to replace all that lower level complexity by raising the level of abstraction and lower the cognitive load for the developer. The developer should be able to just specify a new microservice, give it a name, a description, an owner, say how the backend should be served, the front end should be served, and if it needs a database or not. So the microservice custom resource definition is the API with which the developer will interact, and then a custom microservice operator will be implemented in Java or in Go to start orchestrating things. Instead of that operator directly interacting with the database and Kubernetes containers to enable this, what's often done is to put a layer in between. So you could introduce a front end, a back end, and a database abstraction with each an operator attached to it that will take on that part of a microservice. And so, for example, the database operator will be responsible to provision the schema within Postgres, the user credentials within Postgres, but also activate the backup systems and the auditing stream that's needed for each microservice in your organization. Now, let's dive into some code and show how that will look like. I have a local Kubernetes cluster on my environment, and in it is deployed a Postgres database instance. And as you can see, there are no schemas currently available in it. Also, if I try to get all microservices, which is the custom resource we have defined, there's nothing in there. And also getting all the deployments that are present, nothing is in there. What I have here on top is an example of a new microservice with a name called microservice streaming, description, technical owner, the backend, front end, and the fact that it needs a database. So what I can do as a developer on this platform is to just apply the microservice specification, and what is then shown within the logs of the control plane is that a reconciliation is triggered for that microservice, and it's going to provision a new Postgres schema with this name. So if we refresh the database, then you can see that a schema was created for that database. Also, a user was created and a secret within Kubernetes. The backend is provisioned and the front end is provisioned. So that means that when we have a look at all the deployments that are created, that there are 2 deployments with a container up and running, one for the front end and one for the backend. This is all, these operators are all written in Java. So there's a Java operator SDK available, which allows you to implement a reconciler interface and provides you a reconcile method that's continuously called with the microservice specification that's applied within the Kubernetes environment. And then you can start deploying the backend and the database and so on. Let's take another example from the context of a data engineering task, and more specifically data products within a data mesh. In short, a data product is a component that takes input from its input ports, does a transformation on the data that it gets, and writes it out into its output ports. As such, the developer or the data product developer will interact with the platform in that vocabulary, so data products with input and output ports. All these components are structural elements of a data product. So again, for each of those components, there are a lot of different infrastructure and technologies involved. Examples are, for example, an entry in the data catalog that needs to be provided, or a Spark job that needs to be provisioned for the transformation code. So we again want to abstract away all these details, because a data product is more than just a data set, and provide a level of abstraction that's higher and that lowers the cognitive load. In this case, we introduce the data product as an abstraction, which can again be given a name, an owner, a technical responsible, but also information about what the transformation code will be when it is scheduled, what the input ports are, in this case, a connection to a MySQL database of a source system, and the output ports that need to be provisioned. So again, we raise the level of abstraction to lower the cognitive load. Also, for the design of the platform is a bit similar to the microservice example, in which a developer interacts with the data product custom resource. The data product operator is implemented to start orchestrating, and for each of the sub-components of that data product, different abstractions are introduced on which then more specific operators can interact to provision that Spark job, to provision a data set in BigQuery, and to orchestrate things via, for example, a cron trigger. So to conclude, the goal of platform engineering is to actually raise that level of abstraction so that complexity is hidden. And for this, we use the Kubernetes as a universal control plane to enable this. So this was my talk. Thank you for your attention. And if you want to contact me, please do using the email and LinkedIn details that you see on the screen right now.